Hey guys, we're going to go through banking. To my left, I've got a picture of a Mercedes-Benz, which is going around a bank track, which isn't too high. This is kind of standard. We'll measure that in a minute. And to my right, we've actually got a NASCAR event, and this event it's in Bristol, and this is one of the better ones I've found that has a high banking track. So, alright, so we're going to do a few derivations and we're going to do a few problems. So, you can pay attention and also enjoy the NASCAR as it's playing on to the right. But first of all, let's work out how steep this bank track is on this diagram. So, alright, so what I'm going to do, I'm going to take some measurements. So we're just going to do some approximations. It's not particularly important we get this accurate. So I'm just going to go off the grid as it is. So I'm just going to rule a line here. Okay. And I'm going to presume that on my grid, the vertical lines are directly down. So let's rule that. Actually, let's rule that across. As such. Okay, so we can get a pretty good, so what I've done is pretty much I just follow the kind of the edges of the tires. So you get the edge of the tire here kind of lines up nicely with this point, and the other one lines up over here. So I'm not actually doing any measurements in any particular unit because, well, this is it's a photograph, so it's all to scale. The car's not as big as my. It's small as my screen. So we've basically got 3 squares that way, and I'll just count these ones. 3, 6, 9, 12, 15, 18, 19. 19 across. Let's double check that. 2, 4, 6, 8, 10, 12, 14, 16, 18, 19, yeah. Okay, so we can get a, and our banking angle would fit in here. Alright, so and get a pretty decent estimate as to what that angle might be. Alright, pull out my notepad. Alright, so the angle we can find using tan in particular, tan theta equals opposite 3 over, we said it was 19. Okay, inverse tan. Let's go calculate that. Oops. Get that focus. There we go. Alright, so I've got my calculator off here to the side. Let's find inverse tan. Three divided by 19. So I'm going to round that to pretty much 9.0. Alright. That's really as much as the accuracy as I'm really going to get out of that. Alright, but that's a nice round number anyway, so I like that. Okay, so 9%. In some of the notes you might have read that kind of the, I suppose you can call it, hey, look at those cars on the right, isn't that cool? Yeah, that's a high banking angle, much higher than this. 9 degrees is kind of, that's in the ballpark, that's the correct ballpark, so it's anything up to probably about 12 for just your standard roads. Obviously in the racetrack it's very different. So we've got 9%. Alright. We'll use that later on. Okay, so let's talk about the forces. Alright, so I'm going to draw some force vectors on here. Okay, it doesn't really matter how big they are when you just draw them to start with, so long as you get the kind of relative idea. Alright, so let's turn that around. There we go. Alright, so first thing I'm going to draw is weight. So, okay. Alright. So I lined up my grid so that it would just fit in the middle of this, the Mercedes-Benz icon. Alright, let's draw this down. following that. Okay, and that's my weight force. For the sake of this, I'm going to make it larger than that. I'm going to go right down. It's going to be a nice big diagram. Okay, so that's my weight force going down there. Okay, so that's my force of weight. Well, now the thing about banking tracks is when you got a flat track, and whether the car's moving or it's stationary, the up and down component or up and down vectors must be the same because the car's neither rising nor falling, and the same idea we're placing onto this bank track. But on the flat track, the normal vector is going directly upwards. Now, normal vectors are normal in that the mathematical word normal means that they're at right angles to the surface. Okay, so that's what we're going to draw. Now, for that, I will need my geoliner. Okay, so I can measure the, I can find where the angle is. So basically, I'm going to take that line I drew here for the banked track. So line that up and line that up. And I can move that around till I get a nice right angle. So my right angle is going to point out, see the lines that run across are right angles to the line that's running up here. So I'm actually going to just use this and just put a little point. Let's just adjust that. So I've lined this up so it's over where the red line I drew meets the bank track line that I drew before. Okay, so I'm just going to put a little point here. We'll use that in a minute. Alright, so that's just where the right angle would meet. Okay. Now, what I'm actually going to do first, I'm actually going to measure the weight in terms of these squares. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a nice round number. And then let's just go 10 squares up. Okay, so another color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's count that back. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, displacement of 10 squares. And let's draw that vector. Okay, now the premise of this is the component of the normal force, which is vertical, should match the weight force, otherwise the car is going to kind of slide up and down the ramp, or up or down the ramp, whether it be larger or smaller. And if you watch the NASCAR, well, some of that's happening, but it's because they're traveling too fast and not adjusting with their tires correctly. Or perhaps they're trying to just get along around the outside. Okay, let's try that blue again. Green's nice, so let's go with green. Alright, so that's a vector there. Now, basically what I can do now is I'm going to follow that direction I wrote before. Alright, let's just fix you. No, there we go, autofocus. Okay, I'm going to follow the direction, and the vector I'm going to draw here is the normal force. You can trace it back and it should make a right angle with that, and that's how we designed it in the first place. So just looking over the top, I'm going to draw a normal force that joins the center dot with the dot I drew here, and this is going to go all the way so it's just as high as the one there. So this is actually the normal force. Alright, so that's that there at 1, I've just drawn up here this way. That's your normal force. Okay, normal restoring force. Alright, now let's draw another vector to complete the vector sum to get the vertical and horizontal components. Alright. Alright, so we've got that. That forms a right angle there. Alright, now without going through the great geometry, if you do a bit of geometric proof, you can actually show that that's the same angle there, as the bank track, but that's not something you're going to be assessed on. Okay, you will be assessed on the derivation of the formula for optimal banking. Okay, now the two components here, this component here, that is, okay, that is Fn, so we're shorting that to Fn, Fn cosine theta, and this component up here is Fn sine theta. Okay, we got that. Alright, so now we've got all the vectors that are going on here, including the components of those. Now, I also mentioned weight, just to complete my diagram. Weight is equal to mass times gravitational acceleration. There we go. Alright, so we've got a complete diagram there. So let's just go over the derivation. Okay. Alright, now, as I mentioned before, the vertical component of the normal force has to match the weight. So in other words, the normal force component, cosine theta, that was your vertical part, must equal mg. That's true if the car is not sliding up or down the ramp. Okay. Now, the other part, the Fn sine theta, is at right angles to velocity. So thereby provides you centrifugal acceleration. Okay. So now, let's talk about the two cases. The two situations is you are moving at the correct speed such that you don't require steering, and there's the case that you are not moving at the right speed. So let's start with that one. So non-optimal. Okay, centrifugal force. I should drop the simple for now. Okay, centrifugal force, you've got two things. You've got Fn sine theta, so that's your banking. So it's a component of the normal force is providing centrifugal acceleration, and you add that on with your force of friction, which is your tires. So the force the road provides on the tires when they're angled away from the direction of velocity causes steering. Okay, so both of these are providing centrifugal acceleration. All right, but let's look at the optimal case. Okay, so optimal case, centrifugal acceleration. So optimal case is no friction. Centrifugal acceleration is equal to Fn sine theta. Okay, just to expand, now we've got a formula for centrifugal acceleration. mv squared over r equals Fn sine theta. Okay. Now we also know from up here Fn's cosine theta equals mg. So we're going to use that to simplify this statement, and we can actually cancel out a few things. Alright, now, so I'm going to call that kind of equation 1. That's the first equation you need for the derivation of the optimal formula. And that's equation 2. Alright, so what I'm going to do is I'm actually going to take the left-hand sides of both equations and divide them. So I'm actually going to do equation 1 over... No, sorry, wrong way around. Equation 2 over equation 1. Alright, like this. Fn sine theta over Fn cosine theta equals mv squared on r divided by mg. Okay. Oops. That's what I wanted to do. Okay. Okay, there we go. It's looking pretty. Alright, now, straight away we can cancel these two. Now, if, you should know basic trig, sine theta over cosine theta is equal to tan theta. Okay, we've got that. Now, let's just bring this part together, the right hand side together. That will end up being mv squared on rmg. Okay. So, you can cancel mass. And finally, let's move this so we get a bit more space. So let's move you. Tan theta equals v squared on rg. Okay. Okay, so remembering v is the speed of the vehicle, r is the radius of the track, and g is gravitational acceleration. All right, so let's actually so that's the derivation of the tan theta formula. Before we actually move on to an exercise, I should mention. Okay, so you notice that mass has been cancelled out of this, which is significant. If you build a track to be designed such that you travel at a certain speed, you can design it such that all vehicles, so cars, trucks, and if you wanted bicycles, if they were to travel fast enough, or motorcycles, they will all be able to travel at that speed without requiring friction. That's what we're designing here. Okay, so let's have a go at the question, and let's actually try to bring in our, take it back to our car here. So this car had a 9-degree banking, so we're going to do that, and we're going to have a look at it. I'm just going to put, yeah, it's hard to say exactly where the radius would be, but okay, so I'm just going to be a bit creative with this. It looks like a pretty sharp turn. Okay, so we're going to get creative with this. Alright, so the case is optimal banking. I am going to use the angle of 9 degrees. Okay. And why don't we say that we want to go around that bend. We'll do it for a solution for R. So we've made this, and we wish that cars can travel with a speed of, oh, let's say 80 kilometers per hour. Safely without requiring friction of the tires. Okay, so if they travel a little bit faster than that, they'll need a little bit of steering. If they travel a little bit slower than that, they'll need a bit of steering. So slight adjustments. Okay, so let's take our formula. Tan theta equals v squared on rg. Okay, now we need to change this into meters per second. Let's just pull out our calculator and do that. Okay. So kilometers per hour to meters per second, we have this special relationship of 3.6. So let's just go with approximately. No, this was actually 9.0. 22.2. Alright, so I'm just holding on to a few significant figures until I find my final answer. Okay, so let's move r across. So we'd have r tan theta equals v squared on g, and divide that across. R is equal to v squared on g tan theta. Okay, let's put on our numbers. So we got 22.22 recurring, 9.8, and tan of 9 degrees. All right. Alright, so let's have a look-see. Okay, last answer squared. Divided by bracket 9.8 times tan 9 degrees. Okay, so to travel that fast, the radius of the track would have to be about 318 meters. Okay, there you go. You could round that to 320, and that would make it yeah, pretty safe. All right, so that's a problem involving optimal banking. Okay, there we go. All right, but let's take a non-optimal case. So non-optimal. So we'll say the car travels, we're going to make our velocity equal to 100 kilometers per hour. Okay. We'll say R is still going to be 318 meters. And, yep, use the same angle. Okay, so basically it's the same turn. But the question is now, how much friction is required? So this goes back to force centrifugal equals Fn sine theta plus the force of friction. Okay, so we can solve for the force of friction by basically working out the other two. So you have to work out the normal force, and sine theta is fine because we have the angle. Now, force centrifugal is fine because we actually have, we're missing one thing from this. I'm going to make the mass of the vehicle about 800 kilograms, which sounds fair. Okay. All right, so first of all, let's solve for centrifugal. For centrifugal. Okay, so that's mv squared on r. Okay, now we've got 100, so 100 divided by 3.6. Okay, 27.78. Let's go with that. Let's do that calculation. Let's bring it over here. It's not getting in the way of the NASCAR. All right, 800 times 27.78 squared over 318. All right. Across 1,941 newtons thereabouts. Force centrifugal would be sufficient for this, so I will be obviously incorporating other parts. I'm just going to check. Perhaps I should have actually. I'm doing force and figures. Can I adjust that last answer? Yes, I can. Okay, I'm actually going to change that. Sorry. I should have carried through my last answer. Yeah, it's about that. It actually rounds nicely to a bit more nicely to that value. Anyway, okay, that's good. So picking up some bad habits, but fixing them. All right. Now the thing is about okay, the Fn sine theta part. If we can work out that, then we can work out friction. All right. Now, so to work this out, we need to know Fn. Now, sine theta is fine; we can work that out. But okay, now there's another relationship. You can use Fn cosine theta equals mg. Okay, so you can use that to find what Fn is. So if you divide the cosine across Fn equals mg divided by cosine theta. Okay, got that. Yep. Alright, now let's just go to a new page. Alright, so there's the top. Okay, so Fn, let's focus you. That's better. Fn sine theta, we'll substitute what we just discovered. Replace Fn with mg over cosine theta, sine theta. Alright. Now, we can go and find that is equal to 800 times 9.8 times sine 9 degrees divided by cosine 9 degrees. I know you could say this is all tan 9 degrees if you wish. It's not really that important. Save you one more. A few butter brushes. So 800 times by 9.8 times by sine 9 degrees over cosine 9 degrees. Okay. Alright, so we get this. Alright, rounding to 4 figures, we get 1,242 newtons. Alright. Now, so let's compare that. So that's how much the banking is giving you. What we had over here was how much you actually need in total. Now, if we just subtract those two, we'll have the answer we need. All right. So the force of friction. Upon rearranging that equation, you need this is your total centrifugal force. That's better. Total centrifugal force minus what you get out of the banking. Which I called Fn sine theta. So, our answers were, centrifugal force required was 1,041 newtons minus the banking of 1,242. Alright. So, let's work this out. 1,941 minus 1,242 equals 699 newtons required of friction. Okay, so that's how much the tires need, but obviously you can see just by going a little bit over the design, the optimal design speed, you still get a massive reduction in the amount of, because if you went that fast on a flat track, you would just need the centrifugal acceleration. That's what your tires would have to do, is 1,941. Now your tires just need 699 newtons. Okay. Alright, I hope you guys got something out of that, and yeah, keep working on these questions. So that is banking. So keep watching some NASCAR if you wish.